Yeah. All right, let's go ahead and get started with chapter 21, carboxylic acid derivatives and acyl transfer. When we speak of carboxylic acid derivatives, we're referring to what typically are called acyl compounds. The acyl group refers to the carbonyl with something attached, and then one of these other things attached to it. This is 2 carbons, acetic acid, ethanoic acid. This would be referred to as an acetyl group. That's the methyl group and the carbonyl. And so this is an acetyl group attached to a OH that makes it a carboxylic acid, acid halide, anhydride, ester, nitrile, or amide, whatever. In this chapter, we're going to go through most of these. We did carboxylic acids in the last chapter. And we're going to talk about reactions, and we're going to do mechanisms and stuff like that. This is the mechanism for what's called acyl transfer. But here's a hint. All of these are basically the same mechanism. And that's what's so neat about this. Virtually all of acyl transfer simply involves a nucleophile of some sort attacking the carbonyl of an acyl derivative. This leads to the formation of a tetrahedral intermediate. Okay, so we're going from an sp squared carbonyl to an sp cubed carbon. Tetrahedral, this is our tetrahedral intermediate. Now, we added Y to get to this point. It's an equilibrium. We can move the electrons down, kick Y back out, and we're back here where we started. So it's a simple equilibrium. In order for acyl transfer to occur, when this carbonyl oxygen collapses, we talk about the tetrahedral intermediate collapsing. When it does, the electrons will move back in, and instead of Y leaving, X leaves. So we have transferred the acyl group from X to Y. That's all in the world acyl transfer is. Virtually all of the simple reactions that we're going to look at today, and we're going to do lots of mechanisms, are going to be the same thing. Sometimes we're going to do it a couple times or whatever, but virtually all the acyl transfer reactions are going to use the same basic mechanism. This is very important. It's important that you understand this. We'll look at some rules in a little bit that will let us look at a tetrahedral intermediate, just the intermediate, and predict which of the groups is most likely to be. All right, what we're going to do is run through each of our functional groups and do very quick nomenclature. Once again, nomenclature is not a huge, major part of the second semester of this course, but we do need to know how to name things, and we need to know, what they are. Acid halides. We're going to do our standard thing, drop the E from the parent, and we're going to replace it with an OYL. So instead of acetate, it would be acetyl or ethanoyl. As always, we're going to try to give it the lowest number. We're going to list things alphabetically. And just like we had a special rule for carboxylic acids attached to rings, here we're going to call this a carbonyl halide. So, a couple very simple examples. This is 2-carbon parent, so that's F. It would be Fn because it's fully saturated. and it is an acid chloride, so we would call it ethanoyl chloride. Separate words. This is more properly known, or at least more contemporarily known, as acetyl chloride. Again, it's a derivative of acetic acid, and it's an acid chloride. Over here we have a acid halide attached to a ring. So we're going to use our carbonyl nomenclature. This is going to be a benzene ring with a carbonyl chloride. So benzene, carbonyl chloride. More typically, this is a derivative of benzoic acid. Okay, and again, IUPAC accepts that. Because it's benzoic acid, the name that you typically see is benzoyl chloride. Again, two separate words. Let's just do some quick examples here. Look at these guys and come up with systematic names. In our first one, we're going to find the longest chain containing the acid halide. So that's going to be this guy. We want to give it the lowest number. So we're going to start numbering there. We have 1, 2, 3, 4, 5 carbons. So it's a pentanoyl chloride. And we have an ethyl group attached in carbon 2. 2-ethyl pentanoyl chloride. Over here, we have an acid bromide. Again, we want our chain to contain the acid bromide. We want to give it the lowest number. And since we have a choice, we want this chain with the most substituents. So that's going to be carbon number 1. We have 1, 2, 3, 4 carbons. We have an ethyl group in carbon 2 and a bromine in carbon 3. 3 bromo, 2 ethyl butanoyl bromide. Butanoyl, 4 carbons, and it's an acid bromide. Once again, we have a ring here. So this is going to be a carbonyl chloride. This is a cyclohexene ring. That's going to be carbon number 1. And we would name it as a 2-cyclohexene. So that's 1, 2. And again, it's a carbonyl chloride. And finally, let's just go ahead and name this as a derivative of benzoic acid. That makes it easier. If it's going to be benzoic acid, then this, of course, is going to be carbon 1. It's going to be a benzoyl fluoride. And it's got a methyl in 2 and a bromine down here in 5. 5-bromo 2-methyl benzoyl fluoride. The next group we're going to talk about are acid anhydrides. If we were naming this as a carboxylic acid, once again we would drop the E and we would make it an oic acid. Well, it's an anhydride, so we're going to drop our E and call it an oic anhydride. Same sort of thing, we want to give it the lowest number, list them alphabetically. This is somehow off screen, but this says bis right here. That is what you do if we have a symmetrical anhydride. So if we had two ethyl groups, it would be a bis ethanoic anhydride. This is acetic anhydride. We've used it in lab. Very common reagent. This is ethanoic acid. There are two of them, so it's a bis. So this would be bis ethanoic anhydride. Again, everybody in the world calls this acetic anhydride. Here we have an unsymmetrical, so we need to simply name our pieces. Now we're going to view these as separate words. Here we have an ethyl, so this is a 1, 2, 3. That's a propanoic. This is 2 carbons, so it's either ethanoic or acetic. And again, it's an anhydride. Ethanoic, propanoic, anhydride. 3 words. You could also use more common nomenclature and call it acetic, propionic, anhydride. Propanoic is, of course, preferred, but again, everybody would call this propionic acid. And here's our set. Sure. Our first one here, we have symmetry. We have 1, 2, 3, 4, 5 carbon chains on both. So it's a derivative of pentanoic acid, isn't it? There are 2 of them, so we're going to call it a bis pentanoic anhydride. This is unsymmetrical. We have a 1, 2, 3, 4. That's a bute. So that's a butanoic. 2 carbons. That's ethanoic or acetic. Butanoic, ethanoic, anhydride. Now this guy. You look at this and you should say to yourself, this is a derivative of benzoic acid. Remember, IUPAC likes benzoic acid. It can be apparent. So this is going to be a bis, because there are 2 of them, and it's simply benzoic anhydride. Yeah?
So you can do the bis only because it's symmetrical?
Yep. Yep, only if it's symmetrical. Otherwise, you have to list them out.
So you don't treat it as like a side chain or anything like that?
Nope.
So you're looking at stereochemistry, like if it's together, like superimposed.
Right. Plane of symmetry right down the middle. And finally, this guy. We've never dealt with this. This is a derivative, the 1,2-dicarboxylic acid would be called phthalic acid, PTHALIC. Just like benzoic acid, it's an IUPAC word, and this, instead of being really complex, we're simply going to call phthalic anhydride. Phthalic anhydride. Perhaps you've heard of phthalic acid, plastic bottles, PTE. The P stands for phthalic. Very common polymer. Amides. All we're going to do, instead of calling it an oic acid, is we're going to stick on the word amide. Going to give it the lowest number, do things alphabetically. Now, when we have a nitrogen, we can have two hydrogens, that's a simple amide, or we can have things attached to the nitrogen. If you have something attached to the nitrogen, like a methyl group or anything, any other group, what you do is simply stick this in front with an N. You have to learn to write italic, but N, and then whatever the group is attached to the nitrogen. If you had two of them, it would be N, let's say two methyl groups. It would be N, dimethyl, blah, blah, blah. Two carbon parents, so it's an ethanoic acid. It's an amide. It would be ethanamide. Eth, two carbons, and then we stick on amide. This is known to the world as acetamide. Again, it is a derivative of acetic acid. Here we've taken acetamide and we've put a methyl group on. So this is going to be an N-methyl ethanamide or N-methyl acetamide. Yeah.
Why N again? Because nitrogen?
Yeah.
Okay,
Yeah,
that's what I
this
thought.
means that the methyl group is attached to the nitrogen. Go ahead and look at these. As before, we want our parent to be our 1, 2, 3, 4, 5 carbon chain. We're going to let that be carbon number 1. So it's going to be a pentanamide and an ethyl group dangling off in carbon 2. Once again, our longest, most complex chain is going to be this guy. So we're going to have a 2-ethyl, 3-bromo, and this is 1, 2, 3, 4. So that's a butanamide. Here's our cyclohexene again. Because our amide is attached here, it's going to be carbon number 1. I forgot to point this out from the previous slide, but just like we called it a carboxylic acid, here we call this a carboxamide,
And that's only with rings.
only with rings. Unless, of course, it's a benzene ring, then you're going to do benzoic acid. And finally, speaking of benzoic acid, this is going to be an N-methyl benzamide, isn't it? N-methyl, derivative of benzoic acid, is going to be an N-methyl benzamide. We have a methyl group and a bromine. N-methyl, 5-bromo, 2-methyl benzamide. Now, you know, we're not really going to have on our next exam this big long string of nomenclature. You know that. But as we talk about compounds, we have to be able to call them something. We can't just call them George. So we have to come up with something, right? So let's just make sure that we understand this. Probably most important to be able to take a name and work backwards. Esters. Instead of an oic acid, we're simply going to call this an oate. Instead of having carboxylic acid attached to a ring, we're going to call it a carboxylate. The one thing that you have to do with an ester, remember an ester is an alcohol attached to, our acyl group. So we have to name the alcohol, and we're going to put that name first as a separate word. So if it's a methyl ester, it would be a methyl blah, blah, blah. For example, ethanoic acid again, right? Our alcohol, that's this portion, right here, 2 carbons. So that's ethyl, isn't it? So we simply have to call this ethyl ethanoate. The world would call it ethyl acetate, simple derivative of acetic acid. We've used it in lab over and over again. It's a very nice solvent. It can actually be intoxicating if you inhale too much of it. Used to be in blue. Here we have a methyl ester. Now, this is a 5-member ring, so it's a cyclopentane, isn't it? So it's going to be a cyclopentane carboxylate, but we have to indicate we have a methyl group as our alcohol. So methyl, separate word, cyclopentane, this guy, carboxylate. Go ahead and work our standard set here. Remember, you identify the alcohol, put that as a first word, and then construct the rest. We have our 5-carbon parent, and this is number 1. So it's a pentanoate, isn't it? Our alcohol is going to be methanol, so that's methyl pentanoate with an ethyl group in carbon 2. Remember, the alcohol is a separate word.
So it doesn't even have a dash in between?
Nope, nope, separate word. Our alcohol here is ethanol, so this is going to be an ethyl. This is going to be our chain, carbon 1, going to be a 1, 2, 3, 4, so that's a butanoate. So it's an ethyl butanoate with an ethyl group and a bromine.
Is it only for the carboxylic acid anhydrides that you can put bis in front if it's symmetric? That's the only time? Okay.
All right, our alcohol here is cyclopentanol, isn't it? Cyclopentanol. So that's going to be our first word, cyclopentyl. Again, this is going to be our cyclohexene parent. This is going to be carbon 1, and it's going to be a carboxylate. Cyclopentyl, that's the alcohol, 2-cyclohexene, that's our ring, carboxylate. finally is a derivative of benzoic acid. This is going to be a methyl benzoate with a methyl group and a bromine. Methyl, that's the alcohol, 5-bromo, 2-methyl benzoate.
Dr. Young, what's the longest word, like longest, nomenclature? Is it like 2 sentences or what?
Have you had German?
No.
I have.
Yes, we talk about words. And the last one we're going to have to do is nitrile. So we actually talked a little bit about nitrile last time. We just did some of the reactions. We really didn't do their nomenclature. But it's really simple. Instead of calling it a oic acid or something, we're just going to drop the E and add nitrile to it. Again, we wanted to have the lowest number, list alphabetically. If it's attached to a ring, we're going to call it a carbonitrile. Kind of a funny thing, but that's good. And one more rule on this one. If it's complex, complex molecules, so you have multiple functionalities in there, we're going to, instead of calling it nitrile, we're simply going to say where it is and call it an onitrile. So, let's just look at our set here. We have our 5-carbon thingy here. Oh, I thought my number was going to come up. We have our 5-carbon thingy, so it's going to be a pentane as our parent. Drop the E, call it a nitrile, ethyl group in carbon 2. 2-ethyl pentane nitrile. Here we have our 1, 2, 3, 4 carbon. Again, this is going to be carbon 1, so it's going to be a butane nitrile. Ethyl group, bromine, 3-bromo, 2-ethyl butane nitrile.
So you're not really dropping the E,
No, we're not dropping the E here. If you look at it,
even though it says it.
if we drop, well, you maybe you said that. Sometimes you do, but use your head. If we drop the E out, we would have 2 N's in a row, wouldn't we? And that doesn't make sense. So it's just like back in general chemistry when you did nomenclature of covalent molecules, molecular compounds. Sometimes you would drop the E, sometimes you would not. If you had 2 things together, that's usually bad. Here's our cyclohexene, here's our nitrile, 2-cyclohexene carbonitrile. And finally, our benzoic acid derivative qualifies as a complex molecule. I'm not sure why the distinction, to be honest, but so this is going to be a benzoic acid parent. But because it hits the, quote, complex stage, it's going to be a benzonitrile with a methyl and a bromine. 5-bromo, 2-methyl benzonitrile. So just in summary, carboxylic acids from last chapter, oic acid or carboxylic acid on a ring, acid halides, oleoyl halide or carbonyl halide, whatever halogen you happen to have. We're simply going to call these anhydrides. This is going to be an amide or a carboxamide, depending on ring or not. Going to be a simple O8 or a carboxylate. And finally, we're going to call this a nitrile or an O-nitrile. So it's not going to be a big thing on exams. You know, just make sure that we can communicate. Any questions? All right. We've talked about acyl compounds and carbonyls in the C13. Here we have a very nice distinction between ketones and aldehydes and the acyl carbons. Virtually without exception, simple acyl compounds are in the 170s. Aldehydes and ketones are going to be up here around 200 to 210. I stuck on an alpha-beta unsaturated carbonyl. As you see, the ketone is actually shifted down by the double bond here, but again, it's right up there in the 200 region. In terms of the IR, now we know that carbonyls absorb, we've been saying, around 1700 or so. Acyl derivatives are, of course, carbonyl compounds, and their IR absorbances actually parallel the reactivity of the acyl group very nicely. The higher the absorbance for the carbonyl, the more reactive that particular acyl compound will be. It has to do, think about a carbonyl. We know that carbonyls are electrophilic because we have resonance where we put the electrons on the oxygen and a positive charge here, right? That's what makes them electrophilic. Well, if we stick something that's big and ugly and electronegative directly on the carbonyl, like a halogen, that's going to really suck electrons away from this poor carbon. And it's going to be really reluctant to move them up and make the other resonance form. So that makes that resonance form less important. Bottom line, this winds up to be more double bond character if you have something electronegative attached to it, and so you have a higher energy for the stretch. All the way at the bottom here, we'll see in a minute. Amides, this oxygen has lots and lots of single bond character. Because it has single bond character, it occurs low. Remember, the CO single bond is about 900 or so. So the more single bond character, the lower you go. Acid halides are the most reactive acyl compounds. Then anhydrides, esters, and amides are fairly unreactive. Any questions?
For the second one, how is it 1820 and 17?
We have two peaks.
Okay.
There are two carbonyls. So one is very high, 1820, and the second one appears lower. So if one has less or more double bond character, this has more single bond character.
And so that'll always happen if you have two together?
Yeah, if you have an anhydride, you'll have two peaks, and they're pretty well separated, so you can tell them apart. Nice way to tell an anhydride. All right, when we talk about acyl transfer, like I said on one of the opening slides, what we're going to do is do an addition to the carbonyl carbon to form a tetrahedral intermediate. We've talked about this before. This is our addition-elimination mechanism. If we have something like methyl magnesium bromide, we know that the methyl group is a carbanion. If this is an ester, this would attack, and we would form this as our first tetrahedral intermediate. All in the world that's happening is the methyl anion attacks, makes this bond, carbonyl goes to an O minus. So that's the addition part of our mechanism. The elimination part. Once we make the oxyanion, these electrons can move back in to make a carbonyl, and one of these groups is going to leave. Well, a methyl anion is not going to leave. That's very, very unstable. But methoxide as an anion is much more stable. So it will be our leaving group, and we would generate here an intermediate ketone. Now you remember from the chapter on carbonyls that once we make this ketone, a second mole of Grignard is going to attack, and we're going to wind up with the tertiary alcohol. But as far as addition elimination, this is what we're talking about. Addition to form a tetrahedral intermediate, elimination of one of the groups attached. Down here we have a nitrogen nucleophile. We talked about this also. Again, the nitrogen is going to attack. We're going to wind up with this as a tetrahedral intermediate. Now, one of the things that this tetrahedral intermediate can do is to lose the elements of water to make an imine, or we can move these electrons in and again move this out, just like we did up here, to make, in this case, an amide. So we have addition, tetrahedral intermediate, if somebody leaves, if the nitrogen left, we'd be back where we started, right? So here we let this group leave, and we make the amide. Now, I promised that we would come up with a very simple method to predict which group around a tetrahedral intermediate is going to leave. And it's called partitioning. Let's pretend that we did some addition and that we made this tetrahedral intermediate. If we did, this could break down two ways. We could expel either of the two alkoxides. So the tetrahedral intermediate collapses. When it does, the electrons move back and something leaves. If the methoxide left, we would have a derivative of ethanoic acid. Phenol would be our alcohol, so this would be phenyl acetate. We would also have kicked out our methoxide. So that's one possible product. The other way this can partition is to go this way, and that is kick out the phenoxide. Once again, we can split either of these guys off. This would give us methyl acetate and phenoxide as our second product. All right, so what we're going to do is simply think about what controls which one of these splits off. In general, what you want to do for oxyanions anyway, things that leave as anions, you look at the two thingies and you say to yourself, which one of these is derived from the strongest acid? Okay? Remember what we said about acid strength. What makes something a strong acid is having a stable anion, right? So another way to think about this is the more stable the anion, the more likely it is to leave. Well, let's just do one set of rules here. Whichever group is derived from the strongest acid is going to lead. Now, the methoxide here is derived from ethanol. The phenoxide is derived from phenol. Our pKa's, 16 for methanol, very close to water. 9.4 for phenol. Now, I would give you pKa's, you don't have to remember these. Because phenol is a stronger acid, that means the anion is more stable and it's most likely to leave. Therefore, this is our best leaving group. This is how the intermediate will partition. And we will make methyl acetate and kick out phenol. You look at your two groups. You ask what acid they're derived from. Whichever is the strongest acid will be your most likely leaving group. Let's just do a quick problem. I give you this tetrahedral intermediate. Predict the product. Well, we look at our two possible leaving groups here. One would be a chloride, wouldn't it? And one would be phenoxide. So we're splitting on both sides. Chloride is derived from what acid? HCl. Phenoxide is derived from phenol. HCl at equilibrium gives chloride. Phenol at equilibrium gives phenoxide. We remember from general chemistry that HCl is a strong acid. In fact, its pKa is somewhere between -5 and -10. Very, very strong acid. Phenol, about 9.4. So, our strongest acid here is going to be HCl, which means the chlorine is the most stable anion and the best leaving group. Our partitioning will look like this. Go ahead and quickly write the product.
I didn't know the pK went negative numbers.
Oh, yeah.
No,
Yeah.
From 0 to 15 or whatever.
Nope. You didn't have me for general chemistry, did you?
That's stuff.
There's no bond there.
So, our chlorine is going to leave. We'll make this into a carbonyl. And we have phenyl acetate. Any questions? Now that's nice and simple, isn't it? Now you can look at any tetrahedral intermediate and come up with a real prediction of your product. This is acyl transfer. The nature of the alcohol in acyl transfer for esters not only affects the partitioning, but also affects the overall rate of the reaction. Once again, the more stable the anion, the more likely it is to leave, and therefore it'll leave faster. Therefore, it affects the rate. So look at our collection here. This like electrophilic aromatic substitution. Which of these do you think will be the most reactive ester towards acyl transfer? Remember, we're clipping here, and so we're looking at our phenol as our leading group.
So stable will always be this reactive.
As we've said many, 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 many times now, the more stable the anion, the stronger the acid. Things that stabilize an anion are things that withdraw electrons, right? So in our collection here, the most stable anion is going to be our best electron withdrawing group. That's our nitro. And our least is going to be our electron donating methoxy. So here's our limits. Just like in electrophilic aromatic substitution, quickly make your list. Nitro would be the most reactive, methoxy the least. Here we have a nitrile, that's nice and electron withdrawing. Here we have an acetyl, that's nice and electron withdrawing. This is benzoic acid, that'll be in the middle. And it should look something like that. Any questions? Now, one of the really neat things about being all the way up on chapter 21 is that we've already had lots of functional group chemistry. So we already know, basically, how to make all of these acyl derivatives. And we know, or can easily predict, most of their reactions. So let's just run through history here. Reactions that yield acid halides. We know from our chapter on carboxylic acids that we can take thionyl chloride. Thionyl chloride reacts with a carboxylic acid to make the acid chloride. Another carboxylic acid. We can also make this by what's known as an exchange. Here we're dealing with phosgene, nasty stuff. But we do a simple exchange and make the acid chloride. Those are the two ways that we know to do acid chlorides. We know one way to make an acid bromide, and that was simply PBr3 with the acid. So this is all from the chapter on carboxylic acid. Now, in terms of reactions of acid halides, remember the acid halides are the most reactive of our acyl compounds. The most reactive. They are because the halogen withdraws electrons, puts lots of positive charge on this carbon, makes it very reactive. And it's a very good leading group too. So if we take an acid halide and simply dump it into water, we'll see that that will give us the carboxylic acid. Now we're going to go over each of these. So this is just a summary. If we use an alcohol instead of water, instead of an OH, we're going to put an OR, and that is making an ester. We use a nitrogen compound, we're going to kick out our halogen, make an amide. Now, the last two here, lithiol we know lithium aluminum hydride is a reducing agent, right? In our chapter with carboxylic acids, we said we could add 2 hydrides to the carbonyl of a carboxylic acid. Do the same thing here. We wind up with a primary alcohol. And finally, not surprisingly, a Grignard will add to our carbonyl twice, just like it did for esters, to give us a tertiary alcohol. Now, like I said, this is just a summary to help you remember, so fill it out, and then we're going to talk about each of these. And what I want you to note as we do this is that all of these follow the same basic mechanism. Acid hydrolysis. If we take our acid halide in the presence of water, I made it hydroxide so it's easier. The anion is simply going to attack to give us our tetrahedral intermediate. Now, think about the partitioning. Halogen is going to have a pKa of about -5. Hydroxide has a pKa of almost 16. This is our best leaving group, and we make the acid. Instead of OH, if we add OR, the same thing's going to happen. Oxygen attacks. Here's our tetrahedral intermediate. Our pKa's, once again, -5 and about 16. Halogen is going to leave. And now we made the ester. With a nitrogen nucleophile, we're going to attack. We're going to make our addition intermediate. It looks like this. Now, this would leave as an anion, this would leave as a neutral amine. Turns out that a neutral amine is a better leaving. So this intermediate typically would break down immediately to go back to starting materials. In order for this thing to be stable, we have to lose a hydrogen here to make this intermediate. Now we have a big choice. Big difference. Our pKa here would be -5, right? If this left now, it would leave as an amine anion. And its pKa is about 22. So it's very, very high. Therefore, this is going to leave for sure. And we wind up with the amide. Conversion of our first tetrahedral intermediate conversion of our first tetrahedral intermediate is actually referred to as trapping because it has such a short lifetime. You have to pull this hydrogen off to get here to make this, and then that goes on. So in the lab that we're going to do on Wednesday, we are going to make we are going to do a reaction, I don't want to give it away, between an amine and an acid halide. Okay? Now, we know what's going to happen here. We know that the nitrogen as a nucleophile is going to attack. This is going to be our leaving group. And we're going to make an amide, aren't we? However, if you think about these molecules, we also have an acid chloride sitting here. And if we have amine sitting around, which we will, my gosh, it can happen again, can't it? And it can happen, this can attack one of these guys, this can attack another one, etc., etc., etc. In this case, we make a polymer. This polymer is called nylon 66. This is how they make nylon. 66 because we have 6 carbons here, 6 carbons here. Now, we all know that nylon, a World War II breakthrough, is extremely strong. The reason that nylon is so strong is that we have all these amide groups. Amides can be hydrogen bond donors and acceptors. Remember we talked about hydrogen bonding in carboxylic acids. Same thing. This is a hydrogen bond donor and acceptor. So, if we have strands of our nylon, the spacing is perfect, these guys can line up for these extended hydrogen bonding networks, and that's where nylon gets its strength.
Can I shoot a bullet in it?
Any questions? And again, we're doing this one on Wednesday. All right. We talked about reduction. Remember, hydride is a reducing agent. It's going to donate the hydride to the carbonyl. This is our tetrahedral intermediate. Now, we really don't have a leaving group here, do we? H minus is not going to leave. So X is going to leave. When it does, we make an aldehyde. Think chapter 17. Once you have an aldehyde in the presence of lithiol, you add another one, and you make a primary alcohol. Any questions? Just like hydride, we can also add a carbanion. Remember? Carbanion, our Grignard reagent is going to attack. Once again, we don't have a decent leaving group except for the halogen. Once we make the ketone, another mole is going to add. And once we work it up with acid, we have a tertiary alcohol. Now there's one other cute reaction here that's not actually on our list, but it's a cute reaction. If you take lithium salt and tritert butoxyaluminum hydride, looks like this. Great big ugly thing, isn't it? Has one hydride it can donate. This thing can donate the hydride. We form our standard addition intermediate. Halogen leaves. However, this stuff is so cumbersome that it won't even reduce an aldehyde. So it'll do this because this is more reactive. But once we get to the aldehyde stage, it stops. So it's kind of a neat way to make aldehydes. They're hard to make. My son is sick and I have to go pick him up. Blah, blah, blah. Okay. High maintenance. All right. There is one peculiar reaction. Remember we talked about dialkyl copper lithium reagents a long time ago. We use these for coupling. We react them with alkyl halide, make a big long alkane or something. Not very interesting, really. But it turns out that you can also donate the alkyl group to an acid halide. Only works with acid halides. What happens is this adds, halogen leaves, but instead of giving a carbonyl that you can add more stuff to, the copper actually is the thing that adds to the carbonyl carbon. So we have this intermediate organocopper reagent. This thing undergoes transfer of an R group, copper leaves, and we wind up with the ketone. Kind of a strange reaction, doesn't really follow the pattern, but it's a very interesting reaction and it can be very useful. Finally, if we take an acid halide and react it with a carboxylate anion, not too surprisingly, the oxygen is going to attack. Here we have a halogen, pKa -5. Here we have a carboxylate, pKa around 6, 5 to 6. This is going to leave, and presto, we made an anhydride. This is the easiest and best way to make anhydrides. Any question? Let's put these together into a simple synthesis. We're going to use an acid halide in our synthesis, but we want to start all the way down here with bromobenzene. Now remember, when you do, this is going to be a three-step synthesis. When you do a synthesis, you want to look at, take a peek at your starting material. Okay, you have to peek at it. But you look at your product here, and you say, what is it? How do I know to make it? Well, this is an ester, isn't it? You want to use an acid halide, and so we know that if we took an acid halide and reacted it with an alcohol, we would make an ester. So, draw the structure of the acid halide you would need, and draw the structure of the alcohol. The alcohol portion is this right here, isn't it? That means we are adding isopropyl alcohol. This was our acyl compound, so we need a halogen here, benzoyl chloride, and 2-propanol would work. figure out the alcohol portion, that's this, and then the rest was our acid halide. All right, now we look at this and say, what is this? Well, it's an acid halide, isn't it? And we can make those. We know two ways to make acid chlorides. We could use the bromide, but it doesn't matter. So go ahead and draw the structure of the acid you would need. And of course, you're going to react this with thionyl chloride, SOCl2. The acid, all we're going to do is convert an acid to an acid chloride, benzoic acid, thionyl chloride, and that gets you there. And now finally we have to go back to chapter 20, because we're converting an aryl bromide into a carboxylic acid. Remember, the really cute way to do that was to take a Grignard reagent and react it with CO2. So write the conditions that you would need to convert bromobenzene into benzoic acid. Simply have to make the Grignard, that's magnesium and ether. And then remember, you add little dry ice chips. The Grignard attacks the CO2 to make the acid. Any questions? Make the carboxylic acid, make the acid chloride, make the ester. All right, acid anhydrides. We have fewer reactions here, that's good. Hydrolysis, going to go back to the acid. If we do an alcohol, we're going to add that instead of OH, we'll make an ester. Amines, again, will react and make an amide. And not surprisingly, we can reduce twice with lithal and make the primary alcohol. Same basic set of reactions for all of our acyl compounds. For the hydrolysis, we start off with our anhydride. The oxygen is going to attack one of the carbonyls. This is our tetrahedral intermediate. Think about our leaving groups. Our pKa here, acetate would be 4.6. OH would be about 16, 15.74. Therefore, acetate's going to leave, and we make the carboxylic acid. If we did this with an alcohol instead, same thing. We're going to add. Our pKa's are still about 16 and about 4.6. And we just made, can't see it here, but the ester. Nitrogen is our nucleophile. Nitrogen attacks. We get our zwitterionic intermediate here. we're simply going to lose acetate, and this slightly off screen is the amide. The reduction. Add one hydride. Our leaving group here is going to be the acetate. We now have an aldehyde here. Add our second hydride. And we have the primary alcohol. Same reactions that we had for the alcohol. We talked about esters back in chapter 20. Remember, Fischer esterification. If we take a carboxylic acid and an alcohol, we make a simple ester. Fischer esterification. We can also take the carboxylate anion as a nucleophile and make the ester that way. That doesn't work nearly as well unless it's nicely activated. Fischer esterification is the typical way you would do it. We can also do the diazomethane reaction only to get methyl esters, and you would get this. Diazomethane works very nicely. It's expensive, difficult to use, so you only use it if you really have no other choice. Now, not surprisingly, the reactions of esters are going to be pretty much the same as the reaction of acid halides and anhydrides. If we dump in base, we're going to go from the ester back to the acid. An amine nucleophile, we're going to kick out RO, make the amide. We're going to reduce it, and we're going to add 2 Grignards. That's chapter 17. Our mechanisms here look exactly the same as before. For hydrolysis, our base is going to attack. Now here we have a tie for our leaving group, don't we? Because they both had pKs very close to 16. If hydroxide leaves, we're just back where we started. If alkoxide leaves, however, we go to the carboxylic acid. Simple base hydrolysis. Nitrogen. Again, the nitrogen is going to attack. We have our zwitterion here. We have to trap this by losing hydrogen. Now we have alkoxide, pKa of 16, amine anion 22, 23. Alkoxide is going to leave, and we get the amide. Now, you know, a reaction of amines with esters is actually a very important reaction. This is how you make proteins. Everyone remember transfer RNA. Transfer RNA. Down in this bottom loop, you have a codon that's going to match up with an anticodon in messenger RNA. Messenger RNA has the code for the protein. So these two match up. There is a separate transfer RNA for every amino acid. So they match up. This guy up here, this end, this is an adenine. Here's the sugar. And attached to the sugar, we have an amino acid as an ester. Now the chemistry is just what we just did. Here's our growing peptide chain, protein chain. We have a nitrogen, simply going to attack the carbonyl. This alcohol leaves, and we make a protein. We've added one more, the next one. This guy would be our nucleophile with a new transfer RNA. So very simple, very relevant chemistry. The reduction. Lithiol adds a hydrogen. Lose alkoxide, make the aldehyde, add another hydrogen, and you make the alcohol. Same thing with Grignard. We actually saw this reaction back in chapter 17. We added Grignard, lose alkoxide to make a ketone, add another Grignard, and we have our tertiary alcohol. Any questions? All right, we've worked our way down all the way to amides. Remember, amides are the least reactive. The reason that they're the least reactive is that the nitrogen has this unshared pair of electrons, and it can donate those to the carbonyl. When it does that, this moves the electrons out of the oxygen, and we make this resonance form. This is a very predominant resonance form. The resonance hybrid looks something like this. Partial positive on the nitrogen, partial negative on the oxygen. This is why the CO bond has so much single bond character. That's why it's so unreactive. And it also has one other really neat property. If you think about this resonance form, this is a carbon-nitrogen double bond, isn't it? What do we know about double bonds? Can you rotate around them? Not very well. This is what the orbitals look like. We have a conjugated system here between the two. Here's our negative charge, our positive charge corresponding to these. Because of that, we have a significant barrier to rotation. The amide bond is planar. Because it's planar, this is the thing that gives proteins their kinkiness, if you will. We have this planar amide, and that gives the tertiary structure to the polypeptide chain. There are a couple reactions. If we take an amide, we can do acid-catalyzed hydrolysis. Now you need acid-catalyzed hydrolysis because we have to convert the oxyanion here to a protonated form. Now we can take and add water to this. Here's our tetrahedral intermediate. If we lose a hydrogen here, and lose our amine, we make the carboxylic acid. When you eat protein, this is the amide hydrolysis that occurs as you digest a protein. Again, there are very specific enzymes in your body that catalyze this reaction, even though chemically you need really strong acid and high temperature to do it. They do it obviously at 37 degrees. We can reduce it with lithiol. Now think about this. What are we going to do here? We're going to add one hydride, aren't we? That's going to give us this thing. our leaving group here is actually the oxygen aluminum hydride. Because of that, we can kick it out to make the imine. As we kick it out to make the imine, the carbon-nitrogen double bond, again, is reactive with hydride, and we wind up with the primary amine. Now, there's only one other reaction, amides, that we're going to talk about. Very simple reaction. Well, simple to look at, it's complicated by mechanism. It's a way to go from an amide to a nitrile. What you do is simply warm it up with thionyl chloride, and the reaction goes. All right, this pretty much covers acyl transfer. Again, it's the same chemistry over and over again. And many of the reactions, most of the reactions, we already know. Let's look at some quick problems. If I gave you this tetrahedral intermediate, choose the proper product. pKa's, HCl -5, acetic acid 4.7, phenol 9.4, methanol 16. The strongest acid is going to be your best leaving group, isn't it? This would be HCl, this would be phenol, -5, 9.4. If we lose this is a carbonyl, so we have a 2-carbon parent, that's ethanoic acid. Phenyl group attached for our alcohol, phenyl ethanoate, also known as phenylacetate. Chloride, strongest acid, best leaving group. Do it again. Two acids, HCl and methanol. Chloride, -5, methanol, 16, strongest acid is HCl. When it leaves, this is going to be the acid part, so ethanoic acid or acetic acid. We would have methyl acetate as our product. Any questions? Now you can expect a question or two like this on your exam, because this reflects a bit of sophistication. If you can take a tetrahedral intermediate and predict the products. Identify your two leaving groups.
How do you know there's going to be 2 leaving groups?
Well, we could lose methoxide, we could lose acetate, we couldn't even lose phenylanine, could we? Our two pKa's, acetate, 4.6, methoxide, 16. 4.6 is going to win. That means we're going to have a carbonyl here attached to a benzene ring. That's benzoic acid, isn't it? And here we have methoxy, so that's going to be methyl benzoate. Last one here. Identify your two leading groups. Methoxide, pKa methanol is 16. Phenoxide, pKa of phenol is 9.4. Phenol is the strongest acid. It will be the best leading group. When you clip out your phenol, this is the carbonyl. So you're going to have 2-carbon acid, that's acetic acid. And this is methyl acetate. And let's wind this all up just with a set of reactions that we talked about today. Our first reaction comes straight from chapter 20. Carboxylic acid in the presence of alcohol and acid. Standard Fischer esterification. We're going to convert the acid into the ethyl ester. This is an ethyl group hanging off screen. Our next one, we have an acid anhydride reacting with phenols. We know that anhydrides are reactive. Phenol oxygen will add to one of the carbonyls. We will lose the other half, so that's acetate, and we will make phenyl acetate. If we now take phenyl acetate in the presence of 2 moles of phenyl magnesium bromide, what do we get? We know a Grignard adds to an ester twice. So draw the tertiary alcohol. Now our leaving group here is going to be the phenol, isn't it? So that's gone. That's down the drain. Our tertiary alcohol will have a methyl group and 2 phenyl groups. Wash the phenol down the drain. Carboxylate ester with a primary amine. Just like protein synthesis, isn't it? Nitrogen is going to attack, ethoxide is going to leave. We have a substituent here, so it's going to be an N-methyl amide, isn't it? Here's our peculiar reaction. Acid chloride plus diphenylcopper lithium. Remember, that was odd. We wound up with the copper bond bound to the carbonyl carbon. And then we transfer this one group over, copper leaves, and we make the ketone. We have an amide and we have lithiol. We know what's going to happen. We're going to add hydride to our carbonyl carbon twice. When we do that, we convert this from an amide to a primary amine.
What's at the end of that H?
In H2. And our last two here. This first one, students almost always get this wrong. So make sure you don't. Quickly, just write the products for this. You know what's going to happen. You're going to reduce the carbonyl. You're going to add 2 hydrides to it. When you add 2 hydrides to this carbon right here, what do you get? Ethanol. This carbon is our OH. Ethanol. Such a simple thing, and like I said, people almost always miss it. And finally, chapter 20, carboxylic acid with thionyl chloride. What do you get? An acid chloride. This is a chlorine. Any questions? Yeah.
Do you have any practice problems online, like on Chemistry Online or something, that have something like this?
That's what we just did.
That's
All of,
excellent.
there's
That's it.
no extra, okay.
Dr. Young, your son probably wants you to get Al's practice before it's over. That's why he's texting you.
So I have to run and pick up my son. All right, guys, remember on Wednesday we're doing nylon. I forgot the page number, but it's in there somewhere. And it's called Synthesis of Nylon. Very, very simple reaction, really fun. What you do is you have 2 layers, organic layer and a water layer. And you have the amine in one layer, you have the acid chloride in the other layer. So there's an interface between the 2, right? At the interface, you get nylon form. So you take your glass stirring rod, stick it in so you touch the interface, and then pull it out slowly, and as you do, you make a fiber.
Cool.
It really is neat. All right, see you Wednesday.